When we think of space, we often picture distant galaxies, black holes swallowing stars, or alien worlds light years beyond our reach. But what if I told you some of the most bewildering, head-scratching mysteries aren't out in the deep cosmos? They're hiding right here in our own solar system. Just next door, floating in the silent dark, are wonders so strange they challenge everything we thought we knew about the universe. We've sent probes to every corner of our cosmic neighborhood, and what they've sent back isn't just data, it's a collection of riddles wrapped in enigmas, each one more bizarre than the last. Think about it. We live in a time where humanity is uncovering secrets on moons with erupting ice volcanoes, planets with diamond rain, and magnetic fields that behave in ways science still can't fully explain. These aren't science fiction fantasies, they're real, documented phenomena happening in our celestial backyard, waiting for us to make sense of them. Each discovery pulls back another layer of the extraordinary, revealing a solar system far weirder, more dynamic, and more mystifying than we ever imagined. It's a place where the familiar becomes alien, and the impossible feels tantalizingly close. In this video, we're setting off on a journey to explore 25 of the most peculiar, mind-bending discoveries ever made within our solar system. From the haunting hexagon swirling over Saturn's north pole to the underground oceans that might harbor life on frozen moons, we're going to tour the oddities that defy explanation and ignite our curiosity. You'll witness worlds where the sun never sets, magnetic anomalies that shouldn't exist, and geological wonders that rewrite the rules of physics. So settle in and open your mind. We're about to dive into the beautiful, the baffling, and the downright bizarre lurking just beyond our atmosphere. And we begin our tour of cosmic oddities with a feature so geometrically perfect it seems almost artificial. Hovering over Saturn's north pole is a colossal, swirling hexagon, a storm so vast that the entire Earth could fit inside it. This isn't a fleeting weather pattern. This six-sided jet stream has been raging for decades, possibly even centuries, a permanent and perplexing fixture in the gas giant's atmosphere. It's a meteorological marvel that defies everything we know about weather, where chaotic, swirling vortices are the norm, not stark, angular shapes. So how does a storm form a near-perfect hexagon? Scientists have been wrestling with that question since the Voyager missions first glimpsed it in the 1980s. The leading theory involves deep-rooted atmospheric physics. Imagine a spinning fluid like water going down a drain. Under specific conditions, you can create stable patterns. Researchers simulating Saturn's deep atmospheric currents believe a steep latitudinal gradient in the speed of its winds essentially, a massive, fast-moving jet stream, could create this standing wave pattern. It's like a harmonic resonance, a stable vibration set up in the atmosphere that just happens to manifest as a hexagon. Other theories suggest that a complex interplay of smaller storms, all spinning and jostling for position, could somehow organize themselves into this larger geometric structure through a process of self-organization. What makes the hexagon truly mesmerizing beyond its sheer scale and symmetry is its persistence. Our most powerful hurricanes on Earth dissipate in days or weeks, yet this hexagonal behemoth has outlasted generations of human observation. The Cassini spacecraft provided us with breathtaking, high-resolution views, revealing cloud patterns within the hexagon that whip around its six-sided wall at incredible speeds, yet the overall shape remains stubbornly, eerily intact. It stands as a stunning reminder that the laws of physics can produce phenomena far beyond our everyday experience, a beautiful and enduring puzzle painted in the clouds of a distant world. Leaving Saturn's swirling geometric storm behind, we travel to its largest moon, a world that feels simultaneously alien and hauntingly familiar. Titan is a place of profound paradox, wrapped in a thick, orange haze that hid its secrets from us for centuries. It is the only other place in our solar system besides Earth with stable liquid resting on its surface. But here, the familiar ends. Instead of water, Titan's rivers, lakes, and vast seas are composed of liquid methane and ethane, creating a landscape where the very rocks are likely made of water ice as hard as granite, and the ground is covered in a sludge of organic, sand-like particles. This incredible environment was first touched by human technology in 2005, when the European Space Agency's Huygens probe detached from the Cassini orbiter and began its descent. Plunging through the dense, nitrogen-rich atmosphere for 2.5 hours, it finally landed on a damp riverbed of methane, sending back our first and only photographs from the surface of an outer solar system moon. The images revealed a scene both recognizable and utterly strange, a plain of rounded ice cobbles weathered by flowing liquid under a hazy orange sky. For a brief 90 minutes, Huygens gave us a window into a world that operates on a completely different set of chemical principles than our own. Titan boasts a full hydrological cycle, but it runs on methane instead of water. Hydrocarbon clouds form in its sky, releasing a gentle rain of liquid methane that carves intricate river valleys and feeds great lakes. These bodies of liquid, like the massive Kraken Mare near the North Pole, are thought to be hundreds of feet deep, with waves and currents driven by Titan's winds. The cycle doesn't stop there. Scientists also suspect the presence of cryovolcanoes, ice volcanoes that might erupt with a slush of water and ammonia, adding another layer of complexity to the moon's geology. This active, dynamic system makes Titan a prime candidate in the search for life, though not as we know it. The profound cold at around -290°F makes water ice as solid as rock and liquid water impossible. But what if life could use liquid methane as its solvent instead? The possibility exists for exotic, methane-based life forms with biochemistry fundamentally alien to our own, potentially swimming in those dark, deep seas or dwelling in the subsurface ocean of liquid water that scientists believe exists beneath the ice shell. Titan is a world built from a recipe we thought we knew, but with all the ingredients swapped, presenting us with a second, parallel model of how our active, complex, and maybe even living world can function. And while Titan presents a frigid, hydrocarbon-soaked landscape, our next destination offers a vision of a far more hellish and fiery nature. If you were to stand on the surface of Jupiter's moon Io, you would witness a true spectacle of cosmic violence. This is not a world of quiet, frozen stillness. It is the most volcanically active body in the entire solar system, a place where the very ground beneath your feet is constantly being remade by erupting fire. Io is a world painted in a psychedelic palette of vibrant yellows, deep reds, and stark blacks, a direct result of the sulfur and silicate lava that continually spews from its hundreds of active volcanoes, painting its surface in a fresh, chaotic coat of otherworldly colors. This incredible geological hyperactivity isn't driven by the same internal radioactive decay that powers Earth's volcanoes. Instead, Io is caught in an incredible gravitational tug-of-war. The immense gravity of Jupiter, the solar system's largest planet, pulls fiercely on the small moon. But it's not alone. Io is also yanked and squeezed by the gravitational influences of its sister moons, Europa and Ganymede, as they orbit in a precise rhythmic dance. This constant, rhythmic flexing generates colossal tidal forces within Io's core, much like how you can heat up a piece of metal by bending it back and forth repeatedly. This friction generates immense internal heat, melting rock and creating the tremendous pressure needed to drive lava hundreds of miles up to the surface through volcanic plumes that can shoot over 300 miles into the thin atmosphere. The result is a world in a state of perpetual geological renewal. The Voyager and Galileo spacecraft gave us our first stunning glimpses of this activity, capturing images of massive volcanic eruptions and vast lava lakes that dwarf anything on Earth. New calderas form in a matter of months, and rivers of molten rock flow for dozens of miles, resurfacing the moon so quickly that any impact craters are erased almost as soon as they form. This endless cycle of destruction and creation makes Io a living laboratory for studying extreme volcanism, offering clues about the early, violent histories of all the rocky planets. It stands as a stunning testament to the raw, transformative power of gravity, a force that can mold a distant moon into a breathtaking, churning cauldron of fire and rock. But the solar system's capacity for extreme environments doesn't end with fire. It extends to ice in the most spectacular way. After witnessing the volcanic fury of Io, we arrive at Saturn's brilliant, white moon Enceladus, a world that appears at first glance to be a quiet, frozen billiard ball. Yet this small moon, only 300 miles across, holds one of the most profound secrets in our search for life. From its south pole, Enceladus erupts not with lava, but with colossal geysers of water ice, creating a magnificent plume that shoots hundreds of miles into space and contributes material to one of Saturn's iconic rings. This isn't a rare event. It's a continuous, powerful outpouring from a global ocean hidden beneath an icy shell, a discovery that completely rewrote our understanding of where life could potentially exist. The Cassini spacecraft was the key that unlocked this mystery. As it orbited Saturn, its instruments began detecting something strange. The E-ring, one of the planet's outermost rings, was made of unusually fine ice particles and was being replenished from an unknown source. When Cassini turned its cameras toward the small moon Enceladus, it captured the stunning truth. Gigantic plumes of ice crystals and water vapor were venting into space from a series of massive fractures near the South Pole, nicknamed tiger stripes for their appearance. This revealed that Enceladus wasn't a dead, frozen relic. It was geologically active, with a liquid water ocean trapped between its rocky core and its icy surface. The implications were staggering, and NASA made the daring decision to fly the spacecraft directly through these erupting plumes. On multiple breathtaking passes, Cassini dove through the geysers, its sensors sampling their composition directly. The data sent back was nothing short of revolutionary. The plumes were not just simple water vapor. They contained a fascinating cocktail of ingredients essential for life as we know it. Cassini detected simple organic molecules like methane and carbon dioxide, along with more complex carbon-bearing compounds. Most importantly, it found a high concentration of molecular hydrogen and tiny particles of silica nanograins, which scientists concluded could only be produced by hot water, likely exceeding 190 degrees Fahrenheit, interacting with a rocky core on the ocean floor. This pointed unequivocally to the existence of hydrothermal vents on the seafloor of Enceladus, environments strikingly similar to those on Earth where life thrives in complete darkness, deriving energy not from the sun but from chemistry. This combination of liquid water, a rocky core providing minerals, organic molecules, and a chemical energy source creates an equation that is incredibly compelling for astrobiologists. Enceladus possesses nearly all the ingredients thought to be necessary for life to emerge. Its global ocean, kept liquid by the gravitational squeezing from Saturn, offers a potentially stable environment for billions of years. The constant eruptions provide a free sample delivery service, lofting material from this hidden sea out into space where we can analyze it. This makes Enceladus one of the most accessible and promising places to look for life beyond Earth, a mission that requires not landing on a distant world, but simply flying through the spray of its geysers once more. Future missions are already being planned to return, equipped with more advanced instruments designed specifically to look for the telltale signs of biological activity in those icy particles, seeking an answer to one of humanity's oldest questions: are we alone in the universe? From the spewing geysers of Enceladus, we journey next to a moon that presents an entirely different kind of mystery, one not of hidden oceans but of a surface so violently disrupted it defies simple explanation. Orbiting the icy giant Uranus is Miranda, a small, battered world that looks less like a moon and more like a celestial jigsaw puzzle assembled by a madman. This is not a world of gradual erosion or gentle processes. Its entire surface is a chaotic testimony to some unimaginable cosmic violence, a fragmented landscape that has left scientists utterly baffled since the Voyager 2 spacecraft gave us our first and only close-up glimpse in 1986. Miranda's most striking features are its three gigantic, bizarre regions called coronae. These are vast, trapezoid-shaped areas covered in parallel ridges and grooves, looking almost like a series of enormous racetracks or farm fields etched into the moon's icy crust. The largest of these, named Arden Corona, is a sprawling, complex patchwork of light and dark terrain that stands in stark contrast to the heavily cratered, more typical lunar landscape surrounding it. These features are utterly unique in the solar system, with nothing comparable found on any other moon or planet, making their origin one of planetary science's most enduring puzzles. Even more dramatic are the staggering fault canyons that slash across the surface. Verona Rupes is a cliff face so immense it is often cited as the tallest known cliff in the solar system, plummeting for an estimated 12 miles from top to bottom. To put that in perspective, if you could stand at its edge, the floor of the Grand Canyon would be a mere foothill in comparison, lost in the incredible depth below. So what could have possibly happened to create such a shattered, reassembled world? Planetary geologists have proposed several theories, each more dramatic than the last. The leading idea suggests that Miranda was once shattered to pieces in a catastrophic collision with another large object. After this apocalyptic impact, the moon's own gravity would have slowly and clumsily pulled the fragments back together, haphazardly stacking the pieces into the chaotic geological mess we see today. This would explain the insane juxtapositions of different terrain types and the mind-boggling depth of the canyons, which could be the scars between these poorly fitted chunks of a broken world. Another compelling theory points to intense internal heat, potentially from tidal forces exerted by Uranus's gravity during a past period when the moon's orbit was more eccentric. This heating could have caused massive upwellings of warmer, slushy ice from the interior, distorting the entire surface and creating the coronae as these plumes of material pushed the crust apart, stretching and cracking it into its distinctive ridged patterns before the material eventually cooled and solidified. Miranda remains a frozen snapshot of extreme events, a small world that endured forces powerful enough to tear it apart and reshape it into a bizarre geological collage. Its very existence challenges our notions of how moons behave and evolve, proving that even the smaller, seemingly insignificant bodies in our solar system can hold records of incredible violence and hold secrets we are only beginning to unravel. From the shattered puzzle of Miranda, we venture to a moon that presents a mystery of pure contrast, a celestial body painted in the most extreme shades of black and white imaginable. Circling Saturn is Iapetus, a world so starkly divided that it appears as if two entirely different moons were carelessly fused together. One hemisphere is darker than fresh asphalt, absorbing almost all sunlight that touches it, while the opposite side gleams with the brilliant, reflective brightness of snow-covered ice. This astonishing duality is so pronounced that it was noticed centuries ago from Earth. The 17th century astronomer Giovanni Cassini observed that he could only see Iapetus when it was on one side of Saturn, concluding correctly that one half was profoundly dark and the other dazzlingly bright. For a long time, the origin of this two-faced appearance was one of the solar system's great visual puzzles. The leading theory, now widely accepted, involves an external source, a process of cosmic pollution. The dark material is thought to be a thin layer of dust, likely originating from Phoebe, another of Saturn's moons. Phoebe is dark itself and orbits in the opposite direction to Saturn's other major moons, making it a prime suspect. As micrometeorites bombard Phoebe's surface, they kick up dark debris that slowly spirals inward toward Saturn. Iapetus, plowing through this faint ring of dust like a car driving through a snowstorm, collects this material on its leading hemisphere, the face that is always pointed forward in its orbit. Because Iapetus is tidally locked, always showing the same side to Saturn as it orbits, one hemisphere constantly leads the way, gathering this dark coating over billions of years. But the story doesn't end with a simple dusting. This dark material plays a crucial role in a feedback loop that amplifies the contrast. The dark, dusty areas absorb more solar energy and become warmer than the bright, icy regions. This heat causes any underlying water ice on the dark side to sublimate, to turn directly from a solid into a vapor. This vapor then travels across the moon and refreezes onto the colder, brighter trailing hemisphere and the poles, making those areas even brighter and icier. Over eons, this process has essentially self-cleaned one half of the moon while tarring the other, creating the most dramatic yin and yang in our solar system. Yet Iapetus had another, even more peculiar secret to reveal. When the Cassini spacecraft finally obtained close-up images, it discovered a feature so bizarre it defies easy geological explanation. A massive equatorial ridge that wraps around most of the moon's middle, following its equator with astonishing precision. This mountain range rises over 12 miles high in places, and in some sections is nearly 500 miles wide, giving Iapetus the unmistakable appearance of a giant cosmic walnut. Nothing else like this ridge exists on any other known world, and its formation remains a subject of intense debate. Some scientists propose that the ridge is a fossil structure, a remnant from a time when Iapetus spun much faster than it does today, causing its still-forming crust to bulge outward at the equator and then freeze in place. Others suggest a more catastrophic origin, perhaps the debris from a shattered ring that once encircled the moon, which eventually collapsed and settled onto its surface. Iapetus stands as a world of dual mysteries, a testament to both external forces that can paint a surface and internal processes that can shape it into forms we are only beginning to comprehend. Leaving behind the stark, two-toned mystery of Iapetus, we now travel inward toward the sun, to a world that presents perhaps the most sobering vision of a climate gone horribly awry. Venus, named for the Roman goddess of love and beauty, shines as the brightest, most brilliant object in our night sky after the moon, a beacon of serene beauty. But this appearance is a cosmic deception. Beneath its thick, reflective veil of clouds lies a true hellscape, a shocking example of a runaway greenhouse effect that has transformed a planet once possibly similar to Earth into a crushing, infernal furnace. The numbers alone are enough to defy comprehension. The average surface temperature on Venus is a scorching 867 degrees Fahrenheit, which is hot enough to melt lead and even zinc. The atmospheric pressure at the surface is a staggering 92 times that of Earth's, equivalent to the pressure you would experience nearly 3,000 feet beneath the ocean. This combination creates an environment where a human visitor would be simultaneously crushed, baked, and suffocated in seconds under an atmosphere composed almost entirely of carbon dioxide, with clouds of sulfuric acid drifting through the sky. It is, by every measure, the most hostile planetary surface in our entire solar system. So how did a world often called Earth's sister planet, due to its similar size and mass, become such a terrifying opposite? Billions of years ago, Venus may have been far more hospitable, potentially even possessing shallow oceans of liquid water. But being closer to the sun, it received more solar energy. Scientists believe this initial warming began a fateful process. Any surface water would have begun to evaporate more readily, and water vapor is itself a potent greenhouse gas. This trapped more heat, leading to further evaporation in a vicious, self-reinforcing cycle. This is the runaway greenhouse effect, a feedback loop with no off switch. As the planet grew hotter, vast stores of carbon dioxide that had been locked away in carbonate rocks, as they are on Earth, were baked out and released into the atmosphere through intense volcanic activity. This massive injection of CO2 then trapped exponentially more heat, accelerating the process until the oceans boiled away entirely into space, leaving behind the incredibly dense, choking atmosphere we see today. Another critical factor in this tragic story is Venus's lack of an intrinsic magnetic field. Unlike Earth, which has a spinning iron core generating a protective magnetic shield, Venus's core is thought to have cooled and solidified, stopping that planetary dynamo. Without this shield, the solar wind, a constant stream of charged particles from the Sun, stripped away the hydrogen from what was left of Venus's water vapor over eons. It also steadily eroded the planet's atmosphere, though not nearly enough to counteract the immense volume of gases vomited forth by its volcanoes. This combination of factors, proximity to the Sun, rampant volcanic outgassing, and the absence of a protective magnetic field, sealed Venus's fate, turning it from a potential cradle of life into a permanent cautionary tale. Studying Venus is not just about understanding another world, it holds a profound mirror to our own. It demonstrates with terrifying clarity that a planet's climate is not a guaranteed constant. The delicate balance that makes Earth habitable, our carbon cycle, our plate tectonics that recycle chemicals, our distance from the Sun, and our protective magnetic field is a fragile thing. Venus shows us the ultimate, extreme consequence of a greenhouse effect spiraling out of control. It stands as a stark, silent warning of what can happen when a planet's climate systems are pushed past a point of no return. A reminder of the precious and unique equilibrium we enjoy here on our own blue world. After bearing witness to the crushing, overheated fate of Venus, we might expect the solar system's innermost planet to be nothing more than a scorched and static rock. But Mercury, the Sun's closest companion, holds a startling secret that defies all expectations. Despite its small size and slow rotation, two factors that should make generating a global magnetic field nearly impossible, Mercury possesses one. This isn't just a faint residual magnetism. It's a dynamic, active field, a miniature version of Earth's own protective shield, and it is one of the most perplexing discoveries in planetary science. For decades, the accepted rule was that three ingredients were essential for a planet to cook up a global magnetic field: a core of molten, electrically conductive metal, a rapid rotation to churn that core, and ongoing convection to keep the dynamo process running. Mercury, a planet only slightly larger than our Moon, seemed to fail on all counts. Its rotation is glacial, taking 59 Earth days to complete a single turn. Scientists long believed its small iron core must have cooled and solidified completely billions of years ago, leaving it a geologically dead world. The Mariner 10 flybys in the 1970s offered the first tantalizing hint that this view was wrong, detecting a small but significant magnetic field. But it wasn't until the Messenger orbiter arrived decades later that the true, bizarre nature of this magnetism was revealed. The data from Messenger painted a picture of a magnetic field that was not only real but also deeply strange. First, its strength, while only about 1% that of Earth's, is orders of magnitude stronger than any theory predicted for a planet of Mercury's size. Second, and more bafflingly, the field is profoundly lopsided. Unlike Earth's field, which emerges roughly from the north and south poles, Mercury's magnetic field is offset far to the north of the planet's center. Its magnetic north pole is shifted by nearly 20% of the planet's radius, meaning the entire protective bubble is askew, leaving the southern hemisphere significantly more exposed to the solar wind. This bizarre geometry sent theorists back to their drawing boards. How could such a small, slowly spinning world maintain this mysterious force field? The answer, it seems, lies in the heart of the planet itself. Messenger's precise measurements of Mercury's gravity field and its libration, the slight wobble as it spins, provided the crucial evidence. They revealed that Mercury has a massive iron core, making up a staggering 85% of its radius. And most astonishingly, while the very center of that core may indeed be solid, a large portion of the outer core is still molten. This is the engine for the dynamo, but it operates in a way unlike anything we see on Earth. Scientists now believe the dynamo is powered by a process of chemical snow. As the core slowly cools, iron is crystallizing out of the molten mixture and snowing down onto the solid inner core. This precipitation process, much lighter elements like sulfur being buoyed upwards, drives a slow, lazy convection within the molten outer core. This churning motion of conductive liquid metal, combined with the planet's spin, is just potent enough to generate the weak, off-kilter magnetic field we observe. It's a delicate, almost feeble process compared to the roaring dynamo deep within Earth, yet it is sufficient to create a persistent and enigmatic magnetic presence in the harsh environment so close to the Sun. Mercury's magnetic anomaly is a powerful lesson in cosmic humility. It proves that our models of planetary formation and behavior are still works in progress, and that even the smallest, seemingly simplest worlds can harbor profoundly complex and unexpected interiors. This mysterious magnetism shields a surface etched with another of the solar system's great enigmas, a feature that makes this tiny world look profoundly ancient and utterly unique. This tantalizing trace of methane, a gas so intimately linked with life on our own planet, has become one of the most compelling and frustrating puzzles in modern planetary science. The story begins not with a roar but with a whisper, a faint, intermittent signal first picked up by ground-based telescopes and later confirmed by orbiting spacecraft like the European Space Agency's Mars Express. But it was NASA Curiosity rover trundling through the ancient lakebed of Gale Crater that transformed this whisper into a shout. Its onboard instrument, the tunable laser spectrometer, has been sniffing the thin Martian air for years, and the data it has sent back is a roller coaster of mystery. Methane levels at the rover's location are generally very low, lingering at a background level of around 0.41 parts per billion. But then, without warning, these levels have been observed to spike dramatically, sometimes soaring to concentrations 10 to 20 times higher before vanishing again just as quickly. What makes these methane burps so electrifying is their potential biological connection. Here on Earth, the vast majority of atmospheric methane is produced by living organisms, from microbes in wetlands to the digestive systems of livestock. It's a signature of biology, a gas that doesn't last long in the atmosphere before being broken down by sunlight and chemical reactions. Finding it on Mars immediately raises the breathtaking possibility that we are detecting the breath of Martian microbes, perhaps communities of subterranean organisms living deep within the aquifers beneath the frozen soil. The notion that Curiosity might be parked atop a vast, hidden biosphere is the kind of discovery that would rewrite history. Yet, scientists must be detectives, not poets, and the case for a non-biological or abiotic origin is equally strong. Mars is a geologically active world in its own right, and there are several compelling ways it could be producing this methane without any life involved at all. One leading candidate is a process called serpentinization. This occurs when certain iron and magnesium-rich minerals in volcanic rock, like olivine, come into contact with water. A subsequent chemical reaction produces methane as a byproduct. If liquid water is still interacting with rock deep beneath the Martian surface, it could be steadily feeding methane into the atmosphere. Another geological explanation involves methane clathrates, also known as fire ice. These are icy cage-like structures that can trap methane molecules within them, forming under specific conditions of low temperature and high pressure. Vast reserves of methane could have been locked away in these clathrate deposits billions of years ago when Mars was warmer and wetter. Occasional shifts in the ground, perhaps from small marsquaks or landslides, could then crack these reservoirs open, releasing the ancient gas in sudden, powerful plumes that then dissipate. The mystery is deepened by the fact that Europe's Trace Gas Orbiter, a spacecraft specifically designed with superior sensors to map atmospheric gases globally, has largely failed to detect these same methane spikes that Curiosity measures from the surface. This discrepancy has led to a fascinating scientific detective story. Some researchers propose the rover itself is the source, perhaps releasing the gas from its systems, but this has been repeatedly tested and ruled out. A more likely explanation involves timing and destruction. The TGO makes its measurements high in the atmosphere, and it's possible that the methane plumes are extremely localized and short-lived, being broken down by some unknown process between the surface and the upper atmosphere before the orbiter can detect them. There's even a hypothesis that the methane is being rapidly absorbed and oxidized by the Martian soil itself, a process we've observed in some extreme environments on Earth. This ongoing enigma is precisely why the search for methane source is a central science driver for current and future missions. The Curiosity rover continues its long-term monitoring campaign, building a detailed timeline of the gas's erratic behavior. Its successor, Perseverance, is equipped with even more sophisticated instruments and is exploring Jezero Crater, the site of an ancient river delta, another prime location where signs of past life or its gaseous leftovers might be preserved. The hope is that by correlating methane spikes with other geological and atmospheric data, we can finally pinpoint the origin of this elusive gas. Whether the answer ultimately points to a fascinating geological process we don't yet fully understand or to something far more profound, the hunt for Martian methane represents a perfect example of the scientific method in action, a persistent, careful pursuit of a clue that could lead us to one of the most monumental discoveries in human history. Leaving the enigma of Martian methane behind, we set our sights on the outer solar system to a world that doesn't so much spin as it does somersault through the void. Uranus stands apart from every other planet, not just for its pale, featureless blue-green atmosphere, but for its profoundly bizarre orientation. While every other planet in our solar system spins on an axis that is more or less upright, like a top spinning on a table, Uranus is tipped over onto its side with an axial tilt of a staggering 98 degrees. This means its north pole points almost directly toward the Sun, causing the planet to effectively roll around its orbit like a colossal cosmic bowling ball. This extreme posture creates a seasonal cycle of almost unimaginable extremity. Picture a world where the concept of a normal day and night is completely alien. As Uranus makes its 84-year-long journey around the Sun, each pole in turn is bathed in 42 years of unbroken, direct sunlight. For 4 decades, one entire hemisphere experiences a continuous, searing summer day, while the other half is plunged into a deep, frigid winter night of equal length. Only during the brief periods when the Sun is directly over the equator does the planet experience something resembling a normal cycle of day and night, and even then, the Sun would trace a bizarre, loopy path across the sky. The energy imbalance this creates must drive atmospheric circulation and weather patterns that are utterly foreign to anything we know, a fact underscored by the planet's surprisingly stormy and dynamic atmosphere when we finally got a close look with Voyager 2. The prevailing theory for this astronomical oddity is as dramatic as the tilt itself. Most planetary scientists believe that in the violent, chaotic early days of our solar system, a protoplanet at least twice the mass of Earth slammed directly into a young Uranus. This wasn't a glancing blow, it was a cataclysmic, head-on collision powerful enough to literally knock the planet onto its side. The impactor itself would have likely been absorbed into Uranus's core, which may explain another of the planet's strange features, its composition. Unlike the gas giants Jupiter and Saturn, which are mostly hydrogen and helium, Uranus and Neptune are classified as ice giants, containing a much larger fraction of ices like water, methane, and ammonia. This titanic impact could have delivered a huge amount of this icy material, fundamentally altering the planet's internal structure and density. This ancient catastrophe left a lasting legacy that extends deep into the planet's interior, affecting characteristics we are still struggling to understand. The planet's magnetic field is a perfect example of this lingering weirdness. On Earth, the magnetic field is generated by the churning of molten iron in the outer core and is roughly aligned with our planet's rotational axis. Uranus's magnetic field, however, is a chaotic mess. It is both offset from the planet's center by nearly a third of its radius and tilted at a wild 59-degree angle from its rotational axis. This means the magnetic poles are located nowhere near the geographic poles we would expect. This misalignment suggests that the dynamo generating the field is not happening deep in a well-ordered core, but rather in a shell of electrically conductive material, perhaps a superheated, high-pressure ocean of water and ammonia that is closer to the surface and chaotically churning as the planet rolls along its orbit. The Uranian system, with its strange collection of moons and rings that also orbit in this tilted plane, serves as a permanent monument to that ancient, world-altering violence, a frozen record of one of the most dramatic events in our solar system's history. And from the chaotic, tilted system of Uranus, we turn our attention to a world that presents a vision of serene, frozen perfection, hiding a secret of profound liquid abundance. Jupiter's moon, Europa, is a master of deception. To the casual observer, it is a brilliant, smooth sphere of water ice, crisscrossed by a fascinating web of dark, rusty lines. But this flawless, frozen shell is merely the lid on what may be the single most promising habitat for life beyond Earth in our entire solar system. Beneath an estimated 10 to 15 miles of ice lies a global, liquid water ocean. And this isn't just a small sea. It contains more than twice the volume of all the water in Earth's oceans combined. The first hints of this hidden world came from the Voyager missions, which revealed a surface bizarrely devoid of large craters, suggesting the crust was geologically young and constantly renewing itself. But it was the Galileo orbiter in the late 1990s that provided the compelling evidence. Its magnetometer detected something astonishing. Europa was generating a small, induced magnetic field that periodically reversed direction. The only plausible explanation was a global layer of highly conductive fluid, a saltwater ocean sloshing beneath the ice, interacting with Jupiter's overpowering magnetic field. Further evidence came from the surface geology itself. The moon is a tapestry of fractures, ridges, and chaotic terrains that look like broken ice floes frozen in place. These features strongly suggest a thin, brittle icy shell that is floating on and lubricated by a subsurface ocean, with tidal forces from Jupiter's immense gravity constantly flexing and cracking the surface, allowing warmer, slushy material from below to well up and refreeze. This process isn't always gentle. The Hubble Space Telescope has observed tantalizing evidence of what appear to be enormous plumes of water vapor erupting from Europa's south polar region, much like the geysers on Enceladus but on a potentially grander scale. These sporadic events blast material from the hidden ocean hundreds of miles into space, offering a free sample of the ocean's contents to any passing spacecraft. This discovery electrified the scientific community as it provides a way to taste the ocean without having to land or drill, potentially revealing direct evidence of the chemistry occurring in the darkness below. And it is that chemistry that makes Europa such an compelling target in the search for life. Liquid water is the first and most crucial ingredient, but life also needs a source of energy and the right chemical building blocks. Europa's ocean is thought to be salty, similar to our own oceans, and the reddish-brown material staining the fractures on its surface is likely salts and organic compounds that have welled up from below. But the most exciting prospect is on the ocean floor. Scientists strongly suspect that Europa, like Earth and Enceladus, has hydrothermal vents. These are geysers on the seafloor where superheated water, rich in minerals, erupts from the rocky mantle below. On Earth, such sunless environments are teeming with life, entire ecosystems of tube worms, shrimp, and microbes that derive their energy not from photosynthesis but from chemosynthesis, the process of converting chemicals like hydrogen sulfide into energy. The tidal forces that flex Europa's ice also heat its rocky interior through friction, providing the energy needed to power these vent systems. This creates a complete and potentially sustainable environment for life, liquid water, essential chemistry, and a long-term energy source. Life could have originated around these vents billions of years ago and persisted to this day, completely isolated from the solar system above, thriving in an eternal, dark abyss. The possibility that we could find complex, multicellular life swimming in those depths is not outside the realm of possibility. This incredible potential is why Europa is a prime destination for future exploration. NASA Europa Clipper mission, scheduled to launch in the coming years, is designed to conduct dozens of close flybys, mapping the ice shell in detail, analyzing the composition of the surface, and directly flying through any plumes to analyze their chemistry. Its toolkit of instruments will assess the ocean's depth and salinity and try to confirm the existence of those hypothesized hydrothermal vents. Following Clipper, concepts are already being drawn up for a lander that could potentially touch down on the surface and analyze the surface ice for biosignatures, or even a cryobot, a nuclear-powered probe that could melt its way through the ice shell to finally release a submarine into the alien ocean itself. Europa represents not just a scientific priority, but a profound philosophical quest to descend into the eternal night of an alien sea and discover if we are truly alone in the cosmos, or if life is a much more universal phenomenon than we ever dared to dream. Journeying now from the watery promise of Europa, we travel to the frigid, distant edge of our solar system, to a world that stunned scientists with its unexpected complexity. The New Horizons flyby in 2015 shattered our long-held image of Pluto as a simple, frozen relic. Instead, the spacecraft revealed a breathtakingly diverse world of towering mountains, vast glaciers, and a hazy, layered atmosphere. But one of the most visually striking and chemically fascinating discoveries was the sight of its mountain peaks, not cloaked in white but capped in a beautiful, otherworldly pink. This isn't snow as we know it on Earth. The vibrant, reddish pink dusting on Pluto's high-altitude terrain is actually a form of complex organic molecules called tholins. The name might sound technical, but the process that creates them is a slow, cosmic cooking recipe that begins high in Pluto's thin, extended atmosphere. The primary ingredients are simple gases, methane and nitrogen, which are constantly escaping from the dwarf planet's surface. As these molecules drift high above, they are bombarded by the relentless energy of ultraviolet sunlight from the distant sun and cosmic rays from deep space. This radiation provides the energy needed to break the simple molecules apart and reassemble their atomic components into far larger, more complex polymer-like chains. These newly formed tholin particles are essentially a kind of atmospheric soot or tar, a complex organic gunk that is far too heavy to remain aloft. Slowly, over vast stretches of time, this reddish haze particles drift back down, settling like a fine, colored snow across the entire surface of Pluto. This is why the dwarf planet has its characteristic reddish-brown hue overall. However, this tholin snow doesn't settle evenly. It preferentially accumulates on the highest mountain peaks, much like how snow collects on the tallest mountains here on Earth, creating those stunning, contrasting pink caps against the brighter white plains of nitrogen ice below. This process is a profound form of atmospheric chemistry that has direct parallels to what happens on Saturn's moon Titan, another world where simple gases are transformed by solar energy into a rich soup of prebiotic compounds. On Pluto, the presence of tholins is a clear indicator that the dwarf planet is not a static, dead ball of ice. It possesses a dynamic, albeit thin, atmosphere that is actively interacting with its surface and with space itself, creating a cycle of chemical complexity that scientists are only beginning to understand. These tholins are more than just pretty coloring. They are the building blocks of the complex chemistry that, on a warmer, wetter world, could potentially lead to the formation of life. Finding them in such abundance on a small, cold world at the solar system's frontier dramatically expands our understanding of where the fundamental ingredients for life can form. Pluto's pink snow is a beautiful testament to the fact that even in the deepest freeze, the universe is constantly and creatively cooking up new forms of matter. But the true crown jewel of Ganymede, the feature that truly elevates it to a world of its own, is something no other moon possesses: its own intrinsic magnetic field. This was a discovery that sent shockwaves through the planetary science community when the Galileo probe confirmed it in the 1990s. A global magnetic field is the signature of a dynamic, geologically active interior, typically generated by a churning, molten, electrically conductive core. For a moon to have one is almost unheard of. This means that deep within Ganymede, a hidden engine is running, a core of liquid iron that is still convecting, spinning, and generating a protective magnetic bubble around the entire moon, much like a miniature version of Earth's own dynamo. This creates a celestial dance of incredible complexity because Ganymede doesn't exist in isolation. It is utterly immersed within the overpowering, raging magnetic field of its parent planet, Jupiter. The result is a unique and spectacular phenomenon. Ganymede is the only moon known to have its own set of auroras. As Jupiter's magnetic field sweeps past the moon, it interacts with Ganymede's smaller, weaker field, creating a tangled region of magnetic lines known as a magnetosphere within a magnetosphere. Charged particles from Jupiter are funneled along these lines, striking the thin oxygen atmosphere at the poles and causing them to glow with ethereal ultraviolet light. This constant tug of war between the two magnetic fields doesn't just create a light show. It also pumps enormous amounts of energy into the moon, likely playing a crucial role in keeping its interior warm and its subsurface ocean liquid. And it is that hidden ocean that completes Ganymede's picture as a prime candidate for habitability. Data from Galileo and later from the Hubble Space Telescope provided compelling evidence that Ganymede, like Europa, harbors a vast saltwater ocean buried deep beneath its icy crust. Scientists estimate this ocean could be 60 miles thick, holding more water than all of Earth's oceans combined, and it is sandwiched between layers of ice above and a rocky seafloor below. The presence of a magnetic field is a key clue here, as it suggests a warm interior that prevents the ocean from freezing solid. This sets up the tantalizing possibility that on the seafloor of this alien ocean, where liquid water meets mineral-rich rock and internal heat provides energy, the conditions for life could exist. Ganymede presents us with a world of threefold wonder: a geological record written in light and dark, the heart of a planet beating within a moon, and a hidden sea holding secrets we are only beginning to imagine. From the quiet, frozen beauty of Pluto's painted plains, we now venture to a world of pure, unbridled atmospheric fury. Neptune, the solar system's most distant true planet, presents a profound paradox. Despite receiving only a fraction of the solar energy that warms Earth, its atmosphere is a churning, violent maelstrom of weather, home to the fastest winds ever recorded anywhere. When Voyager 2 raced past this blue giant in 1989, it didn't find a placid, frozen world. It revealed a dynamic and storm-racked jewel, a place where the weather runs on an engine of its own internal fire. The spacecraft's most stunning discovery was the Great Dark Spot, a colossal Earth-sized anticyclonic storm system that bore an eerie resemblance to Jupiter's Great Red Spot, yet was entirely its own phenomenon. This vast, deep blue vortex was a hole in the upper cloud deck, swirling in a counterclockwise direction and accompanied by bright, white companion clouds of methane ice that condensed at its higher altitudes, much like orographic clouds form over mountains on Earth. But unlike Jupiter's centuries-old storm, Neptune's great dark spot proved to be a fleeting giant. When the Hubble Space Telescope turned its gaze to Neptune just a few years later, the storm had vanished without a trace. This transience is a hallmark of Neptune's weather. These immense storm systems can erupt, rage across the planet for a few years, and then dissipate just as suddenly as they appeared, a testament to the incredibly dynamic and changeable nature of its atmosphere. The raw power driving this chaos is almost incomprehensible. Neptune's winds routinely scream at speeds exceeding 1,200 miles per hour, supersonic gusts that could shred any structure and outpace the fastest jet ever built on Earth. These are not simple solar-powered winds. The sun is a tiny, faint disk in Neptune's deep blue sky, far too weak and distant to provide the energy needed for such violence. Instead, this tremendous atmospheric activity is fueled by the planet's own internal heat, a relic from its violent formation over 4 billion years ago. Neptune radiates about 2.6 times more heat energy than it receives from the Sun. This leftover thermal energy, slowly escaping from the planet's deep interior, provides the convection needed to drive those colossal wind speeds and power the formation of its massive, fleeting storms. It's a world running on its own ancient battery, a testament to the powerful forces locked within during the birth of our solar system. The study of Neptune's atmosphere is a lesson in patience and persistence. Without a permanent orbiter, we rely on powerful Earth-based telescopes like Hubble and, more recently, the James Webb Space Telescope to monitor this distant world. Their observations have shown that the disappearance of the original Great Dark Spot was not an end to large storms. In 2018, Hubble spotted another massive dark vortex in Neptune's northern hemisphere, and subsequent observations showed it being accompanied by a smaller storm, suggesting these features may be more common than we once thought. Tracking these evanescent giants helps planetary scientists build better models of atmospheric dynamics, not just for Neptune but for gas giants across the galaxy. This distant blue world, glowing with its own inner warmth, continues to defy our expectations, proving that even in the coldest, darkest reaches of our solar system, the forces of nature can unleash a tempest of breathtaking power and beauty. Far out beyond the orbit of Neptune, in the cold, dark reaches of the Kuiper Belt, spins one of the solar system's most peculiar worlds. This is Haumea, a dwarf planet that defies every expectation of what a planetary body should look like. While most worlds, even small ones, settle into a relaxed spherical shape under their own gravity, Haumea is in a frantic hurry. It completes a full rotation on its axis in less than 4 hours, a spin so blisteringly fast that it can no longer hold itself together as a sphere. Instead, its own centrifugal force has whipped it into the shape of a flattened, elongated ellipsoid, a cosmic football, or perhaps more accurately, a river rock smoothed by a swift current. This bizarre distortion gives Haumea a set of dimensions unlike any other significant body we know of. Based on meticulous observations of its brightness variations and the orbits of its moons, scientists have calculated its shape. It's estimated to be about as wide as Pluto is in diameter along its longest axis, but then dramatically squashed, being significantly shorter on its other axes. If you could stand on its surface, the experience would be disorienting in the extreme. The horizon would curve away at a radically different rate depending on which direction you looked, and the low gravity at its squashed poles would make you feel noticeably lighter than at its bulging equator. This is a world literally stretched to its breaking point by its own rotation, a permanent state of high-speed distortion. The obvious, thrilling question is, what could have possibly caused such an extreme spin? The leading theory is as dramatic as the shape itself, a colossal, ancient impact. Astronomers hypothesize that in the early, chaotic days of the solar system, a large object, perhaps another sizable Kuiper belt object, slammed directly into a proto-Haumea. This wasn't a gentle nudge, it was a cataclysmic event that delivered a tremendous amount of angular momentum, like a cue ball striking another on the cosmic pool table and setting it spinning wildly. The violence of this impact didn't just make Haumea spin, it also had other profound consequences. The collision is believed to have blasted a huge amount of icy debris into space. Some of this debris, held by Haumea's gravity, is thought to have later coalesced to form its two small, swiftly orbiting moons, Hi'iaka and Namaka. The rest of the ejected material is likely the source of the Haumea family, a unique cluster of icy objects sharing similar orbits and surface compositions that now travel along with their parent body, the permanent shrapnel from that defining moment of cosmic violence. Studying such a strange, tumbling world from over 4 billion miles away presents a unique set of challenges for astronomers. We've never sent a probe to visit it, so all our knowledge comes from painstaking observations with the most powerful telescopes on Earth and in space. Scientists must rely on subtle clues, primarily by watching how its brightness changes over time. As Haumea spins, its elongated shape presents a constantly changing surface area to us, causing its reflected light to pulse in a recognizable pattern that betrays its rotation rate and general form. The precise orbits of its two moons provide another crucial data set, allowing researchers to calculate Haumea's mass and, by combining that with its estimated size, determine its density and infer its internal composition. These observations reveal another surprise. Despite its rocky appearance, Haumea is incredibly dense, suggesting it is composed almost entirely of rock with only a thin veneer of water ice coating its surface, a testament to the impact that likely stripped away much of its original icy mantle. Haumea stands as a stunning example of how a single, violent event can define a world for billions of years. It is a frozen record of an impact, a spinning top set in motion during the solar system's infancy that has never slowed down. Its very existence, along with its moons and family of fragments, provides a perfect natural laboratory for understanding the dynamics of collisions and the formation of satellite systems in the outer solar system. This tumbling cosmic egg serves as a powerful reminder that even in the quiet, dark frontier of the Kuiper belt, the history of our neighborhood is written in impacts, spin, and the enduring, strange shapes they leave behind. But our journey through the solar system's dynamic geology doesn't require traveling to distant, icy moons. The evidence for an active, shifting world is written across the rusty surface of our neighbor, Mars. For centuries, we viewed the red planet as a largely static, frozen desert, a world whose geological engines shut down billions of years ago. But modern orbiters have completely rewritten that story, revealing a planet that is, in its own slow and subtle way, still very much alive. Among the most profound revelations is the discovery of active glaciers, not just ancient relics, but features that suggest water ice is still moving and shaping the Martian landscape today. The evidence for this icy activity is everywhere once you know how to look for it. High-resolution images from spacecraft like NASA's Mars Reconnaissance Orbiter show stunningly clear examples of what geologists call lobate debris aprons. These are enormous, flowing sheets of material that extend from the bases of cliffs and crater walls, often stretching for miles across the terrain. Their rounded, tongue-like fronts and telltale flow lines are unmistakable signatures of glacial movement. For a long time, it was debated whether these aprons were made of rock or ice, but ground-penetrating radar has settled the argument. The data shows that these features are not just rock. They are vast glaciers of nearly pure water ice, merely disguised by a thin protective blanket of rocky debris that prevents them from sublimating away into the thin Martian air. Perhaps the most visually dramatic proof comes from the discovery of exposed ice cliffs. In the mid-latitudes of Mars, primarily on steep crater slopes, orbiting cameras have captured breathtaking glimpses of brilliant bluish-white material shining through the ruddy dust. These are sheer faces of water ice, some over 300 feet high, that have been freshly exposed by small landslides or erosion. These gleaming scarps are like natural geological windows, offering us a direct view of the massive frozen reservoirs hiding just beneath the surface. And they are not permanent. By comparing images taken over several Martian years, scientists have watched these ice cliffs slowly retreat as the exposed ice sublimates directly into vapor, confirming that this is an active, ongoing process. This paints a picture of a far more dynamic Mars than we ever imagined. This isn't a planet where water was only present billions of years ago. It's a world with a vast modern-day water cycle centered on ice. The prevailing theory suggests that Mars experiences periodic shifts in its axial tilt, much more extreme than those on Earth. Over cycles of hundreds of thousands of years, the planet's poles can tilt much closer to the Sun, causing the polar ice caps to warm and drive water vapor into the atmosphere. This moisture then travels toward the equator and falls as snow, blanketing the mid-latitude regions in new layers of ice. When the tilt shifts back, this snow is covered and preserved by dust, slowly compressing into the glaciers we see today, which continue to creep and flow under their own immense weight. The implications of this are staggering on two fronts. For understanding Mars's past climate, these glaciers are a frozen record book. By studying their layers and distribution, scientists can decode the history of the planet's dramatic climate swings, learning what caused a once warmer, wetter world to become the freeze-dried desert it is today. But even more exciting are the implications for the future, not of Mars, but of our exploration of it. These widespread, accessible glaciers represent nothing less than a natural resource depot for future human explorers. This is not water locked away in difficult-to-reach polar caps or bound up in minerals. This is nearly pure, mineral water ice, sitting in regions that are far more temperate and easier to land on. This water can be drilled and melted for drinking, used to grow crops, or split into its component hydrogen and oxygen to create breathable air and, most importantly, rocket fuel. The presence of these active glaciers fundamentally changes the equation for human settlement, transforming Mars from a distant, inhospitable outpost into a world with the raw materials needed to sustain life and fuel the journey home. Yet just when we think we've categorized every type of object in our solar system, another one comes along to shatter our expectations entirely. Journey with me now to the space between Saturn and Uranus, where a strange class of celestial nomads known as centaurs wander. These are small, icy bodies with unstable orbits caught in the gravitational crossfire between the giant planets. Among them is one named Chariklo, an asteroid only about 150 miles across. It seemed destined for obscurity, just another frozen rock tumbling in the dark. But in 2013, this tiny world revealed a secret so astonishing it forced astronomers to completely rewrite the rules of planetary science. Chariklo has rings. The discovery was made not by directly imaging this distant speck, but through a clever and precise technique called stellar occultation. Astronomers patiently wait for one of these small, distant objects to pass directly in front of a distant star like a tiny eclipse. By observing how the star's light flickers and changes from multiple telescopes on Earth, they can map out the object's shape, size, and even detect anything surrounding it. On June 3, 2013, teams across South America trained their telescopes on Chariklo as it occulted a star. They expected to see the star's light briefly wink out as the asteroid passed by. But something else happened. Just before and just after the main occultation, the starlight dimmed again in two distinct, sharp dips. The pattern was unmistakable. Something else was blocking the light. After meticulous analysis, the conclusion was inescapable. Chariklo was encircled by two narrow, dense rings. In that moment, this insignificant chunk of ice and rock was catapulted into the record books as the smallest object ever known to possess a ring system. This finding was nothing short of revolutionary. Until then, rings were the exclusive domain of giant planets. The magnificent systems around Jupiter, Saturn, Uranus, and Neptune are all believed to be created and maintained by the immense gravity of these worlds, which can shred passing comets or moons and then shepherd the resulting debris into flat, orderly rings. For a body as tiny as Chariklo, with a gravitational pull barely strong enough to hold itself together, the existence of stable rings is a profound puzzle. How could such a small object acquire rings, and what incredible forces are at play to prevent the material from simply drifting away into space or clumping back together into a moon? The leading theory points to a violent and precise collision in Chariklo's past. Imagine another small object, perhaps a similar-sized centaur, slamming into it. The impact would have been catastrophic, ejecting a tremendous cloud of debris into space around Chariklo. Normally, this debris would either escape entirely or, under the influence of gravity, slowly coalesce to form a new moon. But for Chariklo, scientists propose there must be small, shepherd moons embedded within the rings themselves, their tiny gravitational influence just sufficient to nudge the icy particles, keeping them confined to their narrow, stable paths and preventing them from clumping together. It's a delicate, cosmic balancing act happening around an object so small that its own gravity is almost an afterthought. The rings themselves are fascinating structures. They are incredibly narrow and dense, with one ring measuring about 4 miles wide and the other 2 miles wide, separated by a clear gap of 5.5 miles. They are likely composed of water ice mixed with dark, rocky material, perhaps similar to the composition of Chariklo itself, constantly reflecting the faint sunlight this far from the sun. Their existence suggests that the processes we thought were exclusive to giant planets might be far more common in the solar system than we ever dreamed. If a Chinese letter object like Chariklo can have rings, then perhaps many other small bodies in the distant Kuiper belt or the Oort cloud do too, hidden from our view, just waiting for the precise moment of a stellar occultation to reveal their beautiful, silent halos. Chariklo's rings are a stunning testament to the fact that in our solar system, grandeur and complexity are not reserved for the largest worlds, but can be found orbiting the most humble of objects. And from the silent, icy rings of a distant centaur, we plunge back into the fiery, cloaked chaos of Venus. While its atmosphere presents a crushing, overheated hell, the story written on its surface is one of epic, planet-wide volcanic fury. This isn't a world of subtle geology. It is a canvas of fire dominated by vast volcanic plains that stretch for miles in every direction, covering an estimated 80% of the planet's surface. These are not the familiar, discrete mountains we see on Earth. This is a landscape utterly saturated by ancient lava flows, a testament to a cataclysmic era of flooding eruptions that once resurfaced the entire planet in a relatively short, violent spasm of geological activity. The scale of volcanism on Venus is almost beyond comprehension. Radar maps from missions like Magellan have revealed a world peppered with over 1,600 major volcanoes and countless smaller ones, far outnumbering the volcanic features on Earth. Among them are colossal shield volcanoes that dwarf their terrestrial counterparts. Mons Mott, for example, rises 5 miles high and stretches nearly 250 miles across its base, making it larger than any volcano on Earth except for the massive Olympus Mons on Mars. These giants were built by countless eruptions of low-viscosity lava, slowly oozing from vents and spreading out in thin, expansive sheets over millions of years, gradually constructing these gentle sloping mountains that dominate the horizon. But Venus also showcases forms of volcanism that are utterly alien to our experience. The most bizarre and distinctive are the pancake domes or pharra. These are nearly circular formations, often dozens of miles across but less than a mile high, with incredibly steep sides and a flattened top that gives them their culinary name. Their unique shape is a direct result of the lava that formed them, a much thicker, more viscous type than what built the shield volcanoes. Scientists believe this lava was likely a form of silica-rich rock, such as rhyolite or dacite, which is too sticky to flow very far. Instead, it piles up right over the volcanic vent like thick paste, creating these peculiar, flat-topped mounds that are found nowhere else in the solar system in such abundance. Their presence suggests that Venus's volcanic history involved a much wider variety of molten rock than previously thought, hinting at a complex and evolving geologic past. For a long time, the prevailing theory was that this apocalyptic resurfacing event happened around 500 million years ago, after which the planet's interior cooled and its volcanic engines shut down, leaving it a geologically dead world. But recent evidence has completely overturned that serene picture, suggesting that Venus is not a dormant relic but a world that might still be churning and erupting today. The clues come from careful analysis of data from the European Space Agency's Venus Express orbiter and from Earth-based telescopes. They have detected specific hotspots on the surface, localized areas that appear to be significantly warmer than their surroundings and whose chemical signature suggests they are composed of fresh, unweathered basalt rock. The most compelling evidence for current activity focuses on specific volcanoes like Io Mons and Mons. Infrared sensors have mapped these regions, showing thermal anomalies that seem to trace recent lava flows streaming down their flanks. The logic is straightforward. Venus's corrosive atmosphere, rich in sulfuric acid, would quickly break down and alter the minerals in surface rocks, changing their chemical composition and their ability to emit specific wavelengths of infrared light. The fact that we can see patches that haven't been altered implies they must be very young, perhaps only a few years or decades old, effectively too new to have been tarnished by the hostile environment. This points to eruptions happening not in the distant past but within our own lifetime. This revelation transforms our understanding of Venus from a static warning into a dynamic puzzle. It suggests that the planet's interior is still hot and active, with molten rock periodically finding its way to the surface, much like on Earth. The driver for this activity is likely the same immense internal heat that powers the runaway greenhouse effect in the atmosphere, slowly escaping through the planet's crust. The emerging picture is of a world that may be caught in a continuous cycle, where internal pressure builds up until it is violently released in massive, global volcanic events that periodically repave vast tracts of the surface. Venus is no museum piece. It is a living, breathing, and erupting world, its fiery heart still beating strongly beneath a shroud of clouds, waiting for future missions to finally pierce the veil and witness its volcanic splendor firsthand. Leaving behind the volcanic fury of Venus, we travel back to the serene, frozen beauty of the solar system's outer frontier, where another of Pluto's great mysteries awaits. Among the dwarf planets, many astonishing features revealed by New Horizons. Few are as visually peculiar and scientifically puzzling as the so-called washboard terrain. Found in broad, flat plains like Tartarus Dorsa, this landscape looks less like a world and more like a vast, frozen art installation. An endless series of parallel ridges and troughs meticulously aligned across the horizon, creating a mesmerizing pattern that resembles an enormous washboard or a collection of giant, buried knife blades with their edges pointing skyward. These ridges are colossal in scale, often stretching for hundreds of miles and rising hundreds of feet into Pluto's thin, hazy sky. They are not made of rock but of solid methane ice, a material that behaves in profoundly alien ways under Pluto's extraordinarily cold and low-pressure conditions. The sheer uniformity and vast extent of this terrain presented planetary geologists with a delightful conundrum. What natural process could possibly create such a perfectly ordered, repetitive pattern on a global scale? The answer appears to lie in a combination of Pluto's unique climate cycles and the strange properties of its exotic ices. The leading theory for the formation of this bladed landscape is a slow, persistent process of erosion and sublimation that unfolds over millions of years. Scientists believe it begins with a deposit of methane ice, which may have settled out of Pluto's atmosphere as snow during a different climatic epoch when the dwarf planet's atmospheric pressure was higher and its poles were in a different orientation. This methane snowpack, once laid down, would have been relatively uniform, but as Pluto's climate shifted over eons due to its complex orbital wobbles, the conditions at the surface changed. The sun's feeble warmth, even at its peak, is enough to cause solid methane to transition directly into a gas, a process called sublimation. This is where the mystery deepens into a fascinating dance of physics. The sublimation wouldn't happen evenly across the entire surface. Tiny, initial irregularities in the methane layer, perhaps a small ridge or a dip, would create variations in temperature and sunlight exposure. The peaks of these tiny ridges would sublimate it slightly faster than the troughs, gradually deepening the grooves. This creates a self-reinforcing feedback loop. As the grooves deepen, their shaded sides stay colder and sublimate even more slowly, while the sun-facing ridges continue to ablate away. Over millions of years, this incredibly slow and meticulous process amplifies those initial small bumps into the dramatic, sharp-edged blades we see today. It's a form of erosion, but one utterly unlike anything we see on Earth, sculpted not by liquid water or wind, but by the direct transformation of solid ice into vapor under the gaze of a distant sun. Another compelling theory suggests that these ridges could be a form of penitent, but on a gargantuan scale. On Earth, in the high-altitude deserts of the Andes, suncups called penitents form. These are spikes of hardened snow or ice that can grow to a few meters high, shaped by sublimation under specific conditions of sunlight and cold, dry air. The process on Pluto is thought to be similar but operating over vastly longer timescales and with much harder methane ice, allowing these features to grow to the size of small mountains rather than mere feet. This theory highlights a profound truth about the outer solar system. The same physical principles that shape our own world can, under different conditions, create landscapes of breathtakingly different scales and forms. The discovery of the washboard terrain is a powerful testament to the incredible geological diversity of dwarf planets. It proves that even small, cold worlds at the edge of sunlight's reach are not static, boring balls of ice. They are dynamic, evolving worlds with their own unique geological processes, driven by subtle interactions between their surfaces and their thin atmospheres over immense stretches of time. These frozen blades stand as silent monuments to patience, etched by the slow, invisible hand of sublimation, reminding us that beauty and complexity in the cosmos are not reserved for the warm and the rocky, but can flourish even in the deepest, most eternal freeze. Beyond the familiar procession of planets, another population of worlds moves in secret harmony, locked in a celestial dance with the solar system's largest world. Jupiter is not alone on its orbital path around the Sun. It is forever preceded and followed by vast swarms of ancient asteroids known as the Trojans. These are not scattered randomly through space. They are trapped within gravitational safe havens called Lagrange points, where the combined pull of Jupiter and the Sun creates pockets of perfect stability. Two of these points, known as L4 and L5, lie 60 degrees ahead of and behind Jupiter in its orbit, acting as cosmic parking garages where these primitive objects have been held in stasis for billions of years, preserved like insects in amber from the dawn of our solar system. The Trojans are far from insignificant. They number in the thousands, with the largest members like Hector and Patroclus being well over 100 miles across, essentially small planets in their own right. Despite their numbers and size, they remain incredibly difficult to study from Earth because of their immense distance and a curious surface property. They are profoundly dark. These asteroids reflect very little sunlight, appearing in telescopes as faint, reddish specks against the blackness of space. This dim, ruddy glow is a crucial clue to their composition. The reddish hue is a classic signature of tholins, the same complex organic gunk we saw on Pluto, suggesting surfaces rich in carbon and other life-building elements that have been irradiated and baked by eons of exposure to the sun's energy. They are thought to be some of the most pristine leftovers from the outer solar system's primordial building material, time capsules holding uncontaminated records of the chemistry that eventually formed the giant planets. Recognizing their immense scientific value, NASA launched an ambitious mission named Lucy in 2021. Its objective is nothing less than a grand tour of these ancient fossils. Over its 12-year journey, the Lucy spacecraft is slated to fly by a record-breaking number of asteroids, including one in the main belt and 7 Trojans. This is not a mere flyby mission. It is a systematic reconnaissance of several different types of Trojans, each representing a different class of this primordial population. The mission is designed to conduct a detailed geological and chemical survey, using its suite of instruments to map surface features, determine mass and density, and analyze the composition of these dark, mysterious worlds up close for the very first time. The data Lucy sends back will revolutionize our understanding of the solar system's infancy. By studying the diversity among the Trojans, scientists hope to piece together where in the early protoplanetary disk these objects originally formed. Some may have originated close to Jupiter's current position, while others could have been flung inward from the distant Kuiper belt during the violent planetary migration that reshaped the solar system's architecture. Their current stable orbits are a cosmic accident, a result of being gravitationally captured during this chaotic period, making them a captured sample of material from across the entire early planetary disk. Lucy's mission is to read their individual histories, providing the missing pages to the story of how the giant planets came to be and how they settled into their current orbits, finally giving voice to these silent witnesses that have been trailing Jupiter since the beginning. But as we've just seen with the active glaciers, Mars's icy story is far from over, and nowhere is that more visually stunning than at its very poles. The north and south polar ice caps of Mars are not simple blankets of white. They are dynamic, layered marvels, complex archives of climate history and geological artistry on a planetary scale. These are vast, permanent deposits of water ice, but with a fascinating twist, they are covered by a seasonal veneer of frozen carbon dioxide, what we call dry ice, that comes and goes with the Martian seasons, dramatically altering the appearance of the entire planet from our telescopes. Each pole has its own unique character. The northern polar cap, Planum Boreum, is a sprawling, multi-layered dome of water ice roughly the size of France, buried under a much larger seasonal cover of dry ice that expands in the winter to reach as far south as the mid-latitudes. The southern cap, Planum Australe, is generally colder and retains a more permanent cover of dry ice year-round over its water ice base, though it too undergoes a dramatic seasonal transformation. This seasonal dance is a spectacle in itself. During a hemisphere's winter, as much as 30% of the carbon dioxide in Mars's thin atmosphere freezes out and falls as dry ice snow, creating a brilliant, expansive polar hood. When summer returns, this frozen CO2 doesn't melt, it sublimates, turning directly from a solid back into a gas, retreating to reveal the older, permanent water ice cap beneath. This constant exchange between the atmosphere and the surface is a primary driver of Martian weather, creating winds and pressure changes that ripple across the entire planet. It is within the permanent water ice caps, however, that the true magic lies. Orbiting radar has peered through the surface to reveal that these caps are not solid blocks of ice, but are instead composed of thousands of individual layers of ice and dust, stacked neatly one upon the other like the pages of a book. These are climate records written in frozen strata, each layer representing a different era in Martian history. The theory is that the precise thickness and composition of each layer is a direct response to changes in the planet's orbit and axial tilt over millions of years. When Mars's tilt was more extreme, the poles received more sunlight, causing more ice to sublimate and dust to be deposited. When the tilt was milder, cleaner ice could accumulate. By reading this deep time climate ledger, scientists can essentially reconstruct the history of Mars's wobble and its atmospheric conditions, learning what caused it to transition from a potentially warmer, wetter world to the dry desert it is today. The surface of these icy deposits is just as wondrous as their interior, sculpted into forms that are both beautiful and bizarre. The most striking features are the immense, dark spiral troughs that cut deep into the ice, curving gracefully from the center of the cap toward its edges. These are not canyons carved by liquid water, but are instead the handiwork of two subtle yet persistent forces, wind and sunlight. The prevailing katabatic winds, cold and heavy, flow downslope from the high polar centers. Coriolis forces from the planet's rotation then twist these winds into a spiraling pattern. As they flow, they scour the surface, picking up darker dust particles that absorb more solar heat. This concentrated heat causes the underlying ice to sublimate faster in these scoured paths, deepening and widening the troughs over millennia in a self-perpetuating cycle of erosion. The result is a breathtaking natural work of art, a frozen pinwheel etched into the landscape on a scale that can be seen from orbit. Adding to the polar drama are the colossal chasms that slice through the cap's layers. The most famous of these is Chasma Boreal, a vast canyon in the North Polar Cap that is longer than the Grand Canyon and plunges over a mile deep into the icy deposits. Its origins are still debated. Some scientists believe it was carved by powerful ancient winds, while others suggest it may be a much older feature, a pre-existing valley that was simply filled in and then re-excavated as the ice layers accumulated around it. These chasms act as natural cross-sections, providing scientists with a stunning view of the layered history without needing to drill, exposing the rhythmic banding of light and dark that tells the story of countless climatic cycles. Together, the spiral troughs and deep chasms transform the Martian poles from simple ice deposits into active, evolving geological systems, demonstrating that even in the deepest cold, the forces of wind, sun, and time are forever at work, sculpting the face of another world. But our journey doesn't require traveling to the outer solar system to find bizarre geological activity. Tucked away in the asteroid belt between Mars and Jupiter is Ceres, the largest object in that region, officially classified as a dwarf planet. For a long time, astronomers expected it to be a simple, inert ball of rock and ice, a fossil from the solar system's dawn. But when NASA's Dawn spacecraft arrived in 2015, it revealed a world that was not only complex but astonishingly active, forcing us to completely rewrite our understanding of what an asteroid can be. The most dramatic evidence of this inner life is a singular, towering mountain that rises with impossible steepness from an otherwise smooth plain. This is Ahuna Mons, and it is a geological unicorn, a cryovolcano. This is not a volcano of fire and brimstone, but one of cold and mud. Ahuna Mons stands about 2.5 miles high, a solitary peak that would be impressive even on Earth. Its flanks are not the gentle slopes of a shield volcano. They are remarkably steep and strikingly smooth, scarred by only a few recent landslides, suggesting it is a very young feature in geological terms. Most tellingly, its summit is not a crater but a depression, a clear sign that something once flowed from the top and down its sides, that something was not molten rock but a cold, salty slurry of water ice, mud, and various dissolved salts, a mixture scientists call cryomagma. In the frigid vacuum of space, this briny mud would have oozed out of the volcano's vent and flowed down its sides, immediately freezing solid in the extreme cold, slowly building the mountain layer by frozen layer over time. The existence of such a feature is a profound puzzle. On Earth, volcanoes are powered by internal heat from radioactive decay. For a small world like Ceres, which should have lost its internal heat billions of years ago, to still have enough energy to drive cryovolcanism is a stunning revelation. It points to an interior that is far from dead. Scientists now believe that Ceres contains a large reservoir of briny water beneath its crust, a global ocean in its own right. This isn't a free-flowing ocean like on Europa, but more likely a layer of muddy, salty sludge kept from freezing solid by the presence of antifreeze-like salts, such as hydrated magnesium sulfates. The heat to keep this layer liquid and occasionally drive it to the surface likely comes from the decay of radioactive elements within Ceres's rocky core, a slow and steady trickle of energy that has persisted for billions of years. Ahuna Mons is not the only clue to this active interior. Perhaps the most famous features Dawn discovered are the brilliant bright spots dazzling from within the Ocata crater. These are not reflections, but vast deposits of highly reflective salt, primarily sodium carbonate, that were left on the surface when briny water from below welled up through fractures in the crater floor and then sublimated away, leaving the bright residue behind like a bathtub ring. The stunning clarity and geologic youth of these deposits suggest this process has been happening very recently, perhaps even within the last few million years, which is the blink of an eye on the cosmic timescale. The sheer volume of salt required to create these bright areas points to a vast, region-wide reservoir of brine beneath the crater, a pocket of the larger subsurface ocean that was mobilized by the impact that created Ocata itself. Together, Ahuna Mons and the Ocata bright spots paint a picture of Ceres as a dynamic, evolving world. It is a place with its own unique, cold geological cycle, where internal heat occasionally mobilizes a deep, briny ocean, pushing it to the surface to create mountains and bright plains. This discovery shatters the old view of asteroids as simple, dead rocks. Instead, Ceres stands as a testament to the fact that geological activity and the ingredients for habitability can be found in the most unexpected places, even in the dark, cold reaches of the asteroid belt. It suggests that these small worlds are not merely fossils, but can be complex, layered bodies with their own internal engines, and perhaps even their own stories of water and chemistry that we are only beginning to read. Yet even the chaos of a colliding galaxy pales next to the precision engineering on display within Saturn's magnificent rings. This vast, sprawling disk of ice and rock, stretching over 280,000 kilometers across, is not a uniform sheet of debris. Instead, it's a masterpiece of intricate structure, etched with impossibly sharp gaps and sculpted into perfect waves and spirals. For centuries, astronomers puzzled over how such delicate order could emerge from what should be a chaotic cloud of particles. The answer arrived with the Voyager missions, revealing a cast of tiny, hidden architects, the shepherding moons. These are among the solar system's most peculiar and specialized worlds. Moons like Pan and Daphnis are not the large, spherical bodies we're familiar with. They are small, dense, and oddly shaped, with some resembling giant cosmic ravioli or walnuts. Their defining characteristic is their location. They don't orbit far from the rings, they are embedded within them, traveling in pristine, empty pathways known as gaps. The most famous of these is the Encke Gap, a 325-kilometer wide channel cleared and maintained by the Moon Pan, and the Keeler Gap, a much narrower 42-kilometer lane shepherded by the even smaller Daphnis. The very existence of these clean, empty spaces within a sea of particles was the first major clue to their power. The mechanism is a breathtaking demonstration of celestial mechanics. As these shepherd moons orbit Saturn, their gravity exerts a profound influence on the countless tiny ice particles in the rings nearby. The moon's gravity creates a zone of instability, a region where the gravitational tugs are too strong for a stable orbit. Any ring particle that wanders into this zone is either pulled inward towards Saturn or pushed outward, effectively vacuuming the gap and keeping its edges razor sharp. But the moons do more than just clear a path, they also sculpt the ring material they confines. The gravitational interaction doesn't end at the gap's edge. It creates a resonant dance, pulling on the particles and organizing them into rippling waves that propagate through the rings. The most stunning example of this is the wake created by Daphne's. As this 8-kilometer-wide moon travels through the Keeler Gap, its slight orbital inclination and gravitational pull cause it to literally set the ring material above and below it into an oscillating wave pattern. From afar, it looks as if a tiny moon is swimming through a cosmic pond, leaving a shimmering, corrugated wake in its path that can rise several kilometers above the ring plane. This process is a constant, dynamic tug of war between the forces of accretion and disruption. These moons are themselves likely products of accretion, forming from the very ring material they now command. They exist in a delicate balance. Their gravity is strong enough to control the rings, but too weak to pull the material in and accumulate it into a larger moon. In some cases, they even create their own strange features. Pan, for instance, has gathered ring dust along its equator as it orbits, forming a distinctive ridge that gives it its unique flying saucer or ravioli-like appearance. It's a world literally wearing a belt made from its own construction site. Observing these shepherds at work provides a rare window into the processes that shaped our entire solar system. The elegant gravitational choreography we see around Saturn is a small-scale model of how planets themselves form within the protoplanetary disks around young stars. The same physics that allows a tiny moon to open a gap and shepherd ring particles is what allowed Jupiter to clear its orbital path and prevent a planet from forming in the asteroid belt. These tiny moons are more than just curiosities. They are active participants in the ring's evolution, cosmic sculptors whose gentle gravitational touch carves order from chaos and creates one of the most breathtakingly detailed landscapes in our entire solar system. And just when we thought we had encountered every form of cosmic oddity within our own solar system, the universe delivered a visitor from the vast, uncharted space between the stars, challenging the very definitions we use to categorize objects in the sky. In October 2017, astronomers at the University of Hawaii's Pan-STARRS 1 telescope detected a faint point of light moving at a speed and on a trajectory so extreme it could only mean one thing: this object was not from here. It was the first interstellar object ever observed passing through our solar system, and it was given the name Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. This messenger, however, was in an incredible hurry and behaving in ways that defied all expectations. The initial data revealed a truly bizarre shape. As Oumuamua tumbled through space, its brightness varied dramatically, suggesting an object that was not spherical. By measuring these extreme changes in its reflected light, scientists concluded it was dramatically elongated, shaped like a cigar or a pancake, with estimates suggesting it was up to 10 times longer than it was wide. Nothing of this bizarre proportions exists in our own solar system, where objects, even the most irregular asteroids, tend to be much more rounded by collisions and gravity over time. This was our first clue that the building blocks of other planetary systems could be profoundly different from our own, but the true mystery was yet to unfold. As astronomers meticulously tracked its path, they noticed something inexplicable. Oumuamua was not following a purely gravitational orbit around the Sun. After it whipped around our star and began its journey back out into interstellar space, it was accelerating ever so slightly on a course that could not be explained by the gravitational pull of the Sun or planets alone. This non-gravitational acceleration is a classic signature of cometary activity. As the Sun heats a comet's icy surface, it vents gas and dust, which acts like a natural thruster, gently pushing the object. The catch: Oumuamua showed absolutely no visible signs of being a comet. There was no fuzzy coma of gas and dust surrounding it, no tail streaming behind it. It appeared completely inert, like a bare, dark rock. This paradox-clear acceleration with no visible outgassing ignited a firestorm of debate and scientific inquiry that continues to this day. The leading natural explanation proposes a novel cometary mechanism. Some scientists suggest Oumuamua could have been composed largely of molecular hydrogen ice. This type of ice would sublimate when warmed by the sun, but hydrogen gas is completely invisible to our telescopes. This invisible outgassing could have provided the thrust for the acceleration without creating any visible coma or tail. The catch is that molecular hydrogen ice is only thought to form in the coldest, densest cores of giant molecular clouds, a truly exotic origin story for our visitor. Other theories suggest it could be a chunk of solid nitrogen, similar to the material found on Pluto, with the sun's heat chipping away tiny nitrogen ice particles to provide the thrust. The combination of its strange acceleration, its unprecedented shape, and its interstellar origin led some scientists, most notably Harvard astronomer Avi Loeb, to propose a far more speculative possibility, that Oumuamua could be a piece of alien technology, perhaps a light sail or a derelict probe from another civilization, using the pressure of starlight for propulsion. While this idea captured the public's imagination, the vast majority of the scientific community maintains that an extraordinary claim requires extraordinary evidence, and that a natural explanation, however unusual, is far more likely. The intense debate itself is a testament to the object's truly puzzling nature. Ultimately, Oumuamua's greatest legacy is not in providing answers, but in highlighting the immense gaps in our knowledge. It was a fleeting guest, already too faint to observe by the time its strange properties were discovered, and it is now racing out of our solar system forever, taking its secrets with it. Its brief visit serves as a humbling and thrilling reminder that our solar system is not an island. The galaxy is likely filled with such nomadic objects, and Oumuamua was simply the first one we were lucky enough to spot. It has fundamentally changed astronomy, prompting plans for new telescopes like the Vera C. Rubin Observatory that will actively search for more of these interstellar travelers. The next time one arrives, we will be ready, hoping to unravel the mysteries that our first enigmatic messenger left behind. But our exploration of cosmic oddities isn't confined to the distant reaches of the solar system. One of the most profound and familiar mysteries is literally hanging in our night sky, a world we see nearly every day, yet one that holds a secret in its very posture. Our own moon is tidally locked to Earth, a configuration that means it completes one full rotation on its axis in the exact same amount of time it takes to complete one full orbit around our planet. This synchronicity is why we only ever see one face, the familiar near side, with its patterns of dark Maria and bright highlands. But this locking is more than just a curious coincidence. It's a frozen record of a dynamic, ancient gravitational relationship that has fundamentally shaped the moon's very structure. This state of tidal locking didn't happen overnight. Billions of years ago, when the moon was much closer to Earth and spinning more rapidly, our planet's immense gravity exerted a powerful and unequal pull. Think of the moon not as a perfect sphere, but as a slightly flexible object. Earth's gravity would have tugged more strongly on the side of the moon facing us, creating a subtle, permanent bulge. As the young moon spun, this bulge would never quite align perfectly with Earth. The solid body of the moon would constantly be trying to rotate away, while gravity was relentlessly trying to pull the bulge back into line. This internal friction, this constant tug of war between rotation and gravity, acted like a brake, slowly but surely draining the moon's rotational energy until its spin perfectly matched its orbit. It reached a state of equilibrium, a final sigh where the bulge faced us permanently, and one hemisphere was forever turned away. The legacy of this process is written into the moon's very crust. That persistent gravitational tug is thought to be responsible for one of the most significant geological differences between the two sides. The crust on the far side is significantly thicker by tens of kilometers than on the near side. This disparity had a cascading effect on the Moon's volcanic history. When massive asteroids pummeled the lunar surface in the eons that followed its formation, the impacts punched through the crust. On the near side, where the crust was thinner, these colossal impacts Chinese letter pierced through to the mantle below, allowing vast lakes of molten basaltic lava to well up and flood the giant basins, creating the dark, smooth plains we call Maria. On the far side, with its much thicker armor, the impacts were less likely to penetrate deeply enough to trigger widespread volcanic flows. The result is a surface that remained largely untouched, a primordial, cratered landscape preserved in time. This leaves us with a moon of two starkly different characters. The near side we know is a world of contrast, a mix of battered highlands and vast, frozen seas of ancient lava. The far side, hidden from view until the space age, is a more extreme, uniformly rugged terrain, dominated by the immense South Pole Aitken Basin, one of the largest impact craters in the entire solar system. This bifurcated nature is a direct consequence of that early tidal locking. The Moon's gravitational capture didn't just determine what we see, it dictated the internal thermal evolution and surface geology of an entire world. It stands as a powerful reminder that even the most fundamental relationships, the gentle, constant pull between a planet and its moon, can sculpt a landscape, create eternal duality, and forever hide an entire hemisphere from view, keeping its secrets until we were finally ready to go and see it for ourselves. From the silent, gravitational ballet of Saturn's ring shepherds to the fleeting, tumbling mystery of our first interstellar visitor, we have journeyed past 25 of the solar system's most captivating and bizarre wonders. We have witnessed the hexagonal storm that defies meteorological norms, walked the methane-soaked shores of an alien sea, and felt the volcanic fury of a moon tormented by a giant's gravity. We have descended into hidden oceans that may cradle life and stood before cliffs of ice that tell a billion-year climate story. Each of these discoveries, from the magnetic anomaly of tiny Mercury to the cryovolcanic heart of Ceres, serves as a powerful testament to one overwhelming truth. Our cosmic backyard is a place of endless surprise, a gallery of natural art where the laws of physics paint with a brush far wilder and more inventive than we ever imagined. And yet, for all we have uncovered, these 25 marvels are merely the first few sentences in an epic story we are only beginning to read. Every answered question peels back a layer to reveal 10 new mysteries waiting beneath. The enigma of Martian methane, the hidden engine of Ganymede, the volcanic fires still smoldering on Venus, these are not closed chapters but blazing signposts pointing the way toward the next great era of exploration. They are the puzzles that fuel our insatiable curiosity, driving the engineers and scientists who are right now designing the next generation of missions. The Europa Clipper will soon skim the plumes of that icy moon, while new concepts for Venus landers and Mars sample return missions promise to bring us closer than ever to answers we can barely even formulate as questions today. This relentless pursuit of understanding is what it means to be human. We look up at the silent, star-dusted sky not just in wonder, but with a deep need to know our place within it. Each bizarre discovery, each cosmic oddity, shrinks the vastness of space just a little, transforming the unknown into the known and filling the void with the brilliant light of knowledge. It reminds us that the universe is not a static museum exhibit, but a living, breathing, and evolving system, and we are privileged to be alive at a time when we can actively explore its deepest secrets. So we want to hear from you. Which of these 25 discoveries captured your imagination the most? Was it the potential for life in Enceladus's geysers, the sheer violence of Io's volcanoes, or the perfect geometry of Saturn's hexagon? Let us know in the comments below, and if you enjoyed this journey through the beautiful and the baffling, be sure to subscribe and hit the notification bell so you don't miss our next voyage into the mysteries of space. The adventure is just beginning.